Hey guys, welcome to the PoppySeed Dev Podcast, a show where we break down complex development topics and go deep into the docs, so that you will be well prepared before you start hacking. I'm your host, Aurora PoppySeed, and today we're going to discuss the Mantle network, which is a layer 2 modular network built on top of Ethereum. So yes, that means we're going to go deep into the concept of optimistic rollups, modular blockchains, and data availability, and so on. But all these topics will be discussed in the context of Mantle. So, a huge disclaimer before we get started. I'm not going to be talking throughout this podcast, but instead, a lovely AI voice by the name of Eleanor Sage from 11 Labs is going to do the talking for me. Why so, you ask? Well, mainly because this podcast is currently not sponsored and therefore I cannot dedicate too much of my time into creating and editing it. Gotta get food on the table, guys. But jokes aside, if you are interested in sponsoring this channel or getting in touch with me, either write a comment on YouTube below or connect with me through Twitter. But that said, honestly, I played around with different AI voices, and from all of them, my AI, Eleanor Sage, doesn't really sound that bad. I honestly think she sounds even better than me, but that's up to you to decide. Okay, now, with no further ado, let's get to it.
These rollups rely on an optimistic approach. They assume that the computations are done correctly unless challenged by a fraud proof. There are few key words we have to understand when it comes to the optimistic rollups architecture. 1. The smart contract. This sits on the Ethereum main chain and manages the interaction between the layer 2 rollup chain and the main chain. The smart contract locks user funds deposited for layer 2 transactions, verifies the data submitted by the sequencer, and responds to fraud proofs. 2. Sequencer. The sequencer collects, organizes, and executes transactions on the layer 2 chain. Once a batch of transactions is executed, the sequencer generates a cryptographic proof, Merkle root, of the transactions and submits it to the main chain. 3. Validators. These are nodes that monitor the layer 2 chain, checking for fraudulent activities. If they spot an invalid transaction, they generate a fraud proof and submit it to the smart contract on the main chain. If the fraud proof is accepted, the chain state is rolled back to the previous valid state. The entire system is dependent on the optimistic approach mentioned earlier. When a sequencer submits a batch of transactions, the system assumes they are correct unless a validator submits a fraud proof to challenge it. If the challenge is successful, the sequencer is punished, and the chain state is rolled back to the last valid state. If no fraud proof is submitted within a certain period, for example a week, the transactions are finalized. This approach allows layer 2 transactions to be processed much faster than on the main chain. However, the main drawback is that it requires a waiting period to finalize transactions, especially when users want to withdraw their funds from the layer 2 back to the main chain. This is to allow ample time for potential fraud proofs to be submitted. It's important to note that optimistic rollups are more generalist than zero-knowledge rollups, another layer 2 solution. They can support any smart contract that can be executed on the main chain, which makes them easier for developers to work with. They essentially extend the capabilities of the main chain, allowing more complex applications to be built with lower gas fees and faster transaction times. Having understood Mantle's modular approach and how it addresses scalability and security, let's delve into fraud proofs and how Mantle implements them. But before we do that, let's take a moment to understand what fraud proofs are and what role they play in the world of blockchain and layer 2 solutions. In a blockchain context, a fraud proof is a mechanism used to validate the correctness of a block or transaction. Fraud proofs are particularly useful in layer 2, L2, scaling solutions like optimistic rollups, ORs, where computations are performed off-chain to reduce the load on the base layer, also known as layer 1. In an OR setup, a sequencer processes transactions off-chain and posts the resulting state or state root to the L1 chain. However, this process can be open to manipulation, as there's an inherent trust that the sequencer will act honestly and not post an invalid state. This is where fraud proofs come in. They offer a mechanism for network participants to challenge and prove the incorrectness of the state route submitted by the sequencer, ensuring the system maintains its security and trustlessness. Now let's understand Mantle's implementation of fraud proofs. Mantle, a modular L2 network, employs a fraud-proof system to validate transactions and minimize trust assumptions. In traditional fraud-proof mechanisms, the contract that settles disputes, also known as the on-chain verifier, operates on a lower-level virtual machine such as MIPS or WASM. As a result, an Ethereum virtual machine, EVM client, has to recompile their fraud proof into the lower-level language to be interpretable by the on-chain verifier. This process happens outside the scope of the EVM, leading to potential trust issues. In contrast, Mantle takes a different approach. By compiling and verifying fraud proofs using EVM-level instructions, Mantle allows all Ethereum clients to interact with a common proof system, permissionlessly. This method reduces trust assumptions across verifiers, clients, and compilers. It ensures that the fraud proof's contents are derived directly from a compliant EVM client, and the on-chain verifier is no longer blind to the producer of the fraud proof. Mantle's novel approach to fraud proofs forms a key part of its security architecture. Combined with its decentralized sequencer, Mantle aims to significantly improve the resilience and trustlessness of its network. In Mantle's L2 network, verifiers perform multiple functions. They sync rollup data generated by sequencers, serve it to users and applications, and are incentivized to do so via BIT rewards. They also run contracts with the same state route verification mechanism as L1 contracts and verify the data submitted by sequencers. Most importantly, verifiers perform the essential duty of submitting fraud proofs when they detect an invalid state transition. They use fraud proofs as the evidence of an invalid state transition to initiate the validation process. The verifiers operate within a challenge period, during which any network actor can submit a fraud proof disputing a state they believe to be incorrect. This challenge period is typically around 7 days for most OAuth protocols. To tackle the direct consequence of this challenge period, long withdrawal times, Mantle uses multi-party computation, MPC technology, to verify transaction batches before publishing them to Ethereum. This mechanism reduces the waiting time from 7 days to 1 to 2 days. Mantle uses an interactive fraud-proof system wherein 2 or more parties work in tandem to verify an assertion. One party claims a fraudulent assertion, and the other defends the said assertion. The verifier interacts with the challenger to narrow down the assertion to a single-state transition, which is then verified for its validity. Mantle is further improving its fraud-proof mechanism to compile and execute fraud proofs using EVM-level instructions, thereby eliminating the need for low-level transpiling. This improvement, developed in collaboration with Specular, allows all types of Ethereum clients to interact natively and permissionlessly with a common fraud-proof system, further reducing trust assumptions. Verifiers and fraud proofs form a critical part of Mantle's L2 rollup network, contributing to its decentralization, security, and scalability. With its innovative use of fraud proofs and commitment to enhancing the rollup network's features, Mantle is poised to supercharge Ethereum and build a rich ecosystem of decentralized applications, dApps. For more information on Mantle's technology and plans, you can visit their technical documentation or website. Okay, let's move forward. Having a brief understanding of fraud proofs and how they work in the context of the Mantle network, let's dive deeper into what is the data availability problem and what is Mantle's unique approach to solving it. In the context of blockchain, data availability is about ensuring that all the data necessary to maintain and operate the blockchain is readily available to all network participants at all times. This is fundamental for the smooth functioning of the network and for maintaining its transparency, trust, and security. However, with the increasing scale and complexity of blockchain networks, ensuring data availability becomes quite a significant challenge. This is particularly so in decentralized networks, where data isn't stored in a central location but is distributed across a network of nodes. Consider a Layer 2 solution like a rollup, for example. The rollup processes transactions off-chain, and then posts the aggregated result to the main Ethereum chain. But what if, for some reason, the data associated with these off-chain transactions becomes unavailable? What if a malicious operator withholds the data, or if a node simply goes offline unexpectedly? In such scenarios, the security and integrity of the entire Layer 2 solution could be compromised. Other participants in the network may be unable to verify the correctness of the rollups transactions, which could lead to fraudulent activity or inconsistencies in the blockchain. This is known as the data availability problem. The challenge lies in creating mechanisms that ensure data is always accessible to all nodes in the network, regardless of the scale of the network or the actions of individual nodes. Mantle is addressing this issue using EigenLayer, which leverages the existing Ethereum network to provide data availability guarantees. Data availability is particularly crucial in the context of blockchains that operate on a rollup architecture. This is to eliminate the possibility of block data being withheld, maliciously or otherwise. The reliability of Ethereum's trust network is largely derived from its widespread validator network running a solid consensus algorithm and the relatively well-distributed Ethereum token, ETH. This is where EigenLayer comes in, a unique approach to solving data availability while maintaining security. EigenLayer is a restaking protocol that leverages Ethereum's existing trust network, enabling any rollup-based Layer 2 to guarantee data availability to its execution layer, while maintaining the same level of security as the Ethereum mainnet. It does this through a restaking mechanism where Layer 1 validators can opt in to provide data availability services and are subject to additional performance conditions using their staked Ethereum as collateral. Think of it as an Ethereum middleware platform. Just as optimistic rollups use economic incentives to maintain system integrity, this mechanism also puts incentives in place for Ethereum validators to provide their services for additional yield opportunities. In light of this, Mantle is exploring EigenLayer's data availability solution, known as EigenDA. This implementation allows nodes to provide data availability services to the Mantle network, participate in Mantle's economic model via BIT staking. This not only ensures block data completeness and correctness on the Mantle execution layer, but also takes advantage of Layer 1 security features. An interesting implication of this dual quorum model is the increased staking utility for BIT, in addition to the governance capabilities it offers. EigenDA brings several unique characteristics to the table. It allows for the decoupling of the data availability layer from the consensus layer and employs a unicast channel for data exchange between network participants, delivering efficiency gains both in terms of data transmission and storage. It maintains an erasure rate, which ensures pieces of block data from Layer 2 and Layer 1 sources can be used by verifying actors to reconstruct complete block data. This innovative approach could provide the high throughput necessary for next-generation applications in blockchain gaming, decentralized social networks, and more. Additionally, the Mantle Explorer displays the EigenDA proofs for the rollup data that has been stored on the data availability layer, just as it does for the transactions taking place on Layer 2. In this way, Mantle is taking significant steps in solving data availability issues in blockchain, leveraging the EigenLayer concept and presenting a promising future for blockchain technology. Let me know in the comments section if you want me to do a deeper dive into how exactly the EigenLayer works and what it brings to the table. We've spoken about solving the data availability problem, but there's more to the Mantle story. They've also got their sights set on introducing next-generation trustlessness by decentralizing the sequencer in their optimistic rollups. But first, let's understand what sequencers are. In the context of blockchain and cryptocurrency, particularly within Layer 2 solutions such as optimistic rollups, a sequencer is a specialized node that plays a crucial role in aggregating and ordering transactions. The sequencer's primary function is to take multiple transactions occurring on the Layer 2 network, bundle them together, and then submit this bundle as a single batch onto the base Layer 1 network, like Ethereum. This process is often referred to as rollup of transactions. In traditional setups, there's typically a single sequencer performing these operations, which helps increase efficiency and reduce costs. Because the sequencer batches many transactions together, it significantly decreases the number of individual transactions that need to be directly processed on the slower, more expensive Layer 1 network. This process helps to achieve higher throughput and scalability while still maintaining the security and decentralization properties of the underlying Layer 1 network. A sequencer in Optimistic Rollups is a node that consolidates transactions from the Optimistic Rollup network into batches, which are then submitted to the base Layer 1, L1, Ethereum network. This process effectively allows transactions to occur off-chain on the Optimistic Rollup or network, thereby reducing fees and increasing speed while maintaining the security and trustlessness of the Ethereum network. In the traditional OR setup, there is typically a single sequencer that is trusted to perform these operations. However, having a single sequencer, which is often operated by the Rollups core team, can lead to a degree of centralization where the sequencer could theoretically censor transactions or become a single point of failure. These sequencers give users an immediate soft confirmation that their transactions are included in the block feed destined for Layer 1 recording. To mitigate this issue, Mantle has chosen to implement a decentralized sequencer system within its Optimistic Rollup network. Instead of relying on a single sequencer to batch and submit transactions to the Ethereum network, Mantle aims to have multiple sequencers working within its network, effectively distributing the responsibility of transaction batching across various participants. In Mantle's architecture, anyone can join as a Layer 2 block producer or sequencer and receive rewards for their participation. These sequencer nodes will receive BIT rewards and will be able to also benefit from any miner extractable value, MEV, available through block production. By adopting a structure that supports multiple sequencer nodes, they are striving to bring increased liveness and resilience to the Mantle ecosystem. Their decentralized sequencer architecture takes into account current Layer 2 rollup mechanisms, which predominantly relies on a single sequencer. While such a sequencer can't censor a user's transactions, the need for decentralization remains significant. They aim to achieve two primary goals here. First, anyone should be able to participate in the sequencer set as an L2 block producer. To realize this, Mantle needs to implement a leader election mechanism on Layer 1. A proof-of-stake, POS framework, is a fitting option for this. Secondly, Mantle aims to reduce MEV. For this, each sequencer involved in the consensus process must be able to determine the order of transactions. This necessitates the implementation of a Byzantine fault tolerance, BFT consensus mechanism on Layer 2. Their system strikes a balance between finality and performance by introducing a centralized scheduler to determine which sequencer will produce blocks in the next epoch. The scheduler and the sequencers maintain a communication line to judge the activity of the sequencers and select the next block producer. Their Layer 2 network presents two roles, the scheduler and the sequencer. The scheduler appoints a leader from the sequencer set according to a leadership election mechanism, validates the blocks produced by sequencers, and determines the finality of the blocks. The sequencers are divided into two categories: the leader of sequencers and the sequencer follower. The leader of sequencers is responsible for rolling up the transactions in Layer 2, producing an L2 block, and broadcasting the new block in the sequencer network. The sequencer followers receive the new block from the leader in the correct epoch and execute the transactions in the new block. Now let's pivot to another possible predicament, a sequencer committing an act of malice. The Mantle network is built to address this as well. Rollup verifiers have the ability to detect any invalid block data by verifying state roots. Upon identifying any irregularities, they generate proofs of the malfeasance committed. These proofs can then be presented to smart contracts on the Ethereum network. As a reward for their vigilance, the rollup verifiers receive BIT rewards. This methodology ensures that any malicious act is detected and dealt with promptly, maintaining the security and integrity of the entire network. Having understood the complexities of how the Mantle network operates, we can now transition to the practical aspects. How can you get started with Mantle? Whether you're a developer aiming to deploy your smart contracts or an enthusiast looking to understand its mechanics, we're here to guide you. Next up, we're going to delve into a fundamental aspect of using Mantle, transferring assets. In the realm of blockchain, the process of transferring assets between different blockchains or layers is often referred to as bridging. Similar to a physical bridge connecting two separate landscapes, a blockchain bridge connects two separate ecosystems, facilitating communication and transfer between them. For instance, consider a situation where you need to convert USD to EUR for a trip to Europe. You'd use a currency exchange. Similarly, in the blockchain universe, if you need to move assets or tokens from one blockchain to another, you use a bridge. Why do we need these bridges, you ask? Well, Mantle, as a Layer 2, L2 solution, functions as a distinct blockchain system separate from Ethereum, L1. Just as you'd require an exchange platform to convert your USD to EUR, you need a mechanism to move ETH and other tokens from Ethereum to Mantle, ensuring it's done in a secure and verifiable manner. This is where the Mantle Bridge comes in, offering a convenient pathway for assets to move in and out of the Mantle network. Bridges can be divided into two primary types: trusted bridges and trustless bridges. Trusted bridges rely on a central entity for their operations, while trustless bridges use smart contracts and algorithms for their operations, minimizing trust requirements and enabling users to remain in control of their assets. However, as bridges are still evolving, they come with inherent risks, including smart contract bugs, technological failures, and potential hacks. The process of moving assets between Mantle and Ethereum, often referred to as bridging, is enabled by Mantle's official bridge. This bridge facilitates the transfer of tokens between Mantle and Ethereum and even allows the creation of Layer 2 representations of existing Ethereum tokens. The Mantle bridge consists of a set of smart contracts on both Ethereum and Mantle. When you send a deposit request for, say, 10 BIT from Ethereum, these tokens get locked in the Ethereum contract, and an equal number of BIT tokens are minted on Mantle and transferred to your wallet. The process is reversed when you want to withdraw from Mantle to Ethereum. The BIT tokens on Mantle are burned, and the same number of BIT tokens locked in the Ethereum contract are released and transferred to your wallet. You can easily make these deposits and withdrawals by connecting your wallet to the Mantle bridge. However, if you wish to use the Bridge API, you can refer to the Mantle Bridge API documentation for more information and tutorials on how to use the appropriate SDK methods for bridging various tokens. To sum up, the Mantle Bridge offers a secure and reliable medium for transferring assets between Ethereum and Mantle, which further enhances the usability of Mantle's Layer 2 solutions. But it's essential to remember that while bridges bring an impressive range of convenience and functionality, they also introduce their own risks. Therefore, always exercise due diligence when moving assets across networks. Now that we've successfully transferred our assets, let's shift our focus to the developers in our audience. We'll guide you through how you can get started by diving into the Mantle documentation. For developers, the process of deploying contracts on Mantle isn't much different from deploying your smart contracts on any other Ethereum Layer 2 chains. Your first step towards interacting with Mantle will be connecting to the Mantle testnet. The official test network of Mantle is known as Mantle Wadsley, and you can find essential details like the chain ID on Mantle's official page. A crucial aspect of Mantle's testnet is acquiring test bit, the native token of Mantle. Mantle has established a bit faucet on Ethereum's Gurley testnet. This faucet has an ERC20 implementation of BIT, along with a method that mints tokens for the caller. However, it's necessary to have a bit of Gurley ETH, denoted as Geth, to pay the gas fee for minting testnet bit. If you're in need of Gurley ETH, faucets like MetaMask or MyCrypto can provide some. Once you've got your testnet bit, you can use the testnet bridge. This bridge, available on Gurley, facilitates the deposit of BIT from Gurley. Just go to the testnet bridge, select Deposit Bit from Gurley, and add the Gurley testnet bit contract address to your wallet. You can use this same bridge to withdraw BIT tokens from Mantle back to Ethereum's Gurley testnet. Now that we've covered the basics, let's take a closer look at the Mantle Software Development Kit, or SDK. The Mantle SDK provides a comprehensive suite of features, including inter-network message passing, token deposit and withdrawal between Layer 1 and Layer 2 networks, creation of ERC20 tokens on Layer 2, mapping to Layer 1 token, and monitoring of contract calls and messages. The SDK's modules make it easy to connect the Mantle network to wallets, exchanges, and other applications. To wrap up this Getting Started guide, remember that decentralized applications, or dApps, require access to nodes to fetch block data and send transactions. Mantle provides this access through its Node API, which supports Ethereum's JSON RPC API implementation. This API can be accessed using HTTPS and WebSocket. More information about using the Mantle Node API can be found on Mantle's official Node API page. Whether you're a developer looking to integrate your smart contracts or a curious enthusiast eager to dip your toes into the blockchain waters, Mantle provides a user-friendly and innovative platform to explore. Stay tuned as we delve deeper into Mantle and other intriguing blockchain technologies in our future episodes. Well, dear listeners, we have come to the end of yet another enlightening episode of the PoppySeed Dev Podcast. We hope that today's dive into Mantle, its mechanisms, and the how-tos of getting started have been both educational and inspiring. As developers and enthusiasts in this ever-evolving tech world, we continuously encounter new frontiers and innovative platforms like Mantle. They challenge us to learn, adapt, and in turn, shape the future of blockchain technology. Remember, the initial steps can seem complicated, but with resources and guides available, starting with Mantle isn't an insurmountable task. So whether you plan to develop sophisticated smart contracts or simply wish to understand the workings of Ethereum's Layer 2 solutions, Mantle provides an excellent learning ground. Thank you for joining us on this journey today. Your curiosity and eagerness to learn are what drives this podcast. We hope to see you in our next episode, where we'll continue our journey, exploring more fascinating topics in the world of blockchain and decentralized technology. Until then, happy coding!